In this video, I'm going to wrap up the nodal analysis for AC section and also introduce mesh analysis or loop analysis for AC. Alright, I'm going to kick this off with an example number 1, and this is an example in which we're going to use nodal analysis, and I'm actually going to make it a little easy on you because I'm going to start in the phasor domain already. Alright, so I've got a 2 amp source minus J4 ohms on this capacitor. I've got a nice resistor here, it's 4 ohms, and then I've got probably the meanest thing, a voltage source up here, 16 angle 45 degrees volts, and then a inductor which is J8 ohms, and then a resistor here which is 16 ohms. Alright, and then the other thing I'm going to do is I'm going to go ahead and specify V1 and V2, and I want you to find for me V1 and V2. Alright, so the first thing I should notice is that I have what's called a supernode. A supernode. Alright, so a supernode is anytime I have a voltage source between two nodes where both of them are not ground. So that's what this 16 angle 45 degree volt source is. Now, because of that, I know that I have some special superpowers which we'll come to in just a minute. Before I do that, I need to make sure I go through all my steps. So remember, I'm using PAAST, or my past, to do this. So some sort of weird time travel movie we've got going on where we're going back to the past. But here's the deal. First thing is phasor transform. That's done. Second thing is to assign. Also done. So I'm to step 3, which is just to apply. All right. So in the apply step, normally I go node by node, but when I have a supernode, I have a couple of special rules. So the first is that I get a constraint equation at the supernode. Constraint equation at the supernode. All right, so I've got V1 minus V2 equals to 16 angle 45 degrees. Where do I come up with that, you may ask? Well, I'm so glad you asked. I'm going to take the positive of the voltage at the plus side and minus the voltage at the minus side and set those equal to the voltage in between. That's where the constraint equation comes from. The next thing I do is that I apply KCL at the supernode. Alright, KCL at the supernode says that if I imagine this whole thing here as one big node, then I can do KCL into and out of that. Now, one of the other special secret powers of a supernode, which I like to draw like this. This is my supernode. What a powerful being. Alright, one of the very powerful things about that is that it's going to ignore anything in parallel. So let's go ahead and make that ignorance. And remember that current is always going to go from a larger voltage to a smaller voltage, and I'm assuming V1 is bigger than V2 is bigger than 0. So I've got my 2 amp source coming in. I've got the current through this negative J4 ohm capacitor going out, so minus V1 minus 0 over negative J4. And then I've got the current through the J8 inductor, so minus V2 minus 0 over J8. And then the current through the 16 ohm resistor, so minus V2 minus 0 over 16 equals to 0. And then all I need to do is make this a little bit cleaner. So how am I going to do that? Well, first thing I can do is move my j's to the top. Minus j becomes j, so I've got 2 minus j v1 over 4. Then I've got a positive j here that becomes negative j when I move it up top. So the negatives cancel and I get plus j v2 over 8. And then minus v2 over 16 equals 0. If I multiply everything by 16, what that gives me is 32 minus j4 v1 plus j2 v2 minus v2 equals to 0. If I collect these terms together, I've got 32 on one side, and on the other side I've got j4v1, and then I've got plus 1 minus j2 v2. That's my second equation. So I've got both equations, both of them coming from the supernode. Now, step 4 is to solve. Now, I could do this algebraically. I don't really want to, but I absolutely can. So I'm just going to put it in matrix form. And then you can go back on your own, solve it algebraically, make sure you get to the same place. But here's what the matrix form version of this is. I've got 1 minus 1, and then I've got j4 and 1 minus j2. This is v1 v2 is equal to 16 angle 45 degrees, and this is just 32. And then I can plug this into Python or MATLAB and get my answer. Now, if I take this, if I want to put this into Python or MATLAB, I've actually got to do the following. So I would say, at least in MATLAB, I would do 16 times the cosine in degrees of 45 degrees plus 16 times I, so 16i, times the sine d of 45 degrees. Because I've already done that, I know I'm going to get 11.31 plus j 11.31. So when I plug that in, I'm going to get the following. I'll get v1, v2 is equal to 29.9 angle negative 73.2 degrees and 40.03 angle negative 93.8 degrees. Now, step 5 is normally go to the time domain, but if you recall in the beginning of this example I said find v1 and v2 in phasor form, so I can actually stop at this point. Now, if you can't get to the same place using algebra, you've done it wrong, and that's the time to contact me and ask me some questions. Alrighty. Anything else about nodal analysis? We've done a regular nodal analysis problem in the previous example, and now we've done the nodal analysis example with a supernode in this video. So now it's time that we can work on our next phase, which is mesh analysis. Mesh analysis. Alrighty, we're again more or less using the exact same rules as DC, but we slap one additional step. We slap one additional step on there first, that's the phasor transform, and one at the end, which is the time domain transform. So let me remind you, assign in this case is saying we're assigning loop currents. Apply Kirchhoff's voltage law and solve for loop currents. That's what's happening in mesh or loop analysis. So we're going to apply this immediately to an example. We'll call it example number 2. Here we go. So I've got the following. I've got a current source, which is 4 angle 0 degrees. I've got a J8 ohm inductor with a negative J4 ohm capacitor. We'll call this one a 5 ohm resistor. We're going to have a source here, which is 10 angle 90 degrees. From the center point, I've got minus J5 ohms. This one's just going to be 10 ohms. Combine those together. And then what I want to do is find I naught in the phasor form. I naught is going to be defined as the current right there. All right, solution. First thing we do is phasor form. That's done. Next thing we do is we assign. So let's do that. I'm going to call this one, this loop current I1, this one I2, and this one I3. And what I want to highlight is that I naught is just equal to negative I2. So if I can find I2, then I am done. All right, so let's move on. Step 3 is to apply Kirchhoff's voltage law. Let's look at loop number 1. In loop 1, I have an independent source right here. Goodness, that's sloppy. But I have an independent source that doesn't touch any loops, and the type of source it is current. So I know the current in that loop has got to be the same as I1. So I1 is equal to 4. Whew. All right, in loop number 2, that's this big loop here, I have the following. I have 5I2 for the 5 ohm resistor plus 10 angle 90 degrees. We'll work with that here in a minute. Minus J5. I2, so this is the capacitor here. I2 is the direction I'm going in. I3 is opposite, so I2 minus I3. Minus J4. I2 minus I1, same logic. And all of this has to equal up to 0. Now, let's highlight the following. 10 angle 90 is just J10. Just making sure we capture that here. The other thing I can do is I can sub in equation 1 and collect my terms. So I know that I1 is 4, so I've got 5I2 plus J10 minus J5I2 plus J5I3 minus J4I2, and then plus J4 times 4. All of this equaling to 0. All right, so this is J16, that's J10. Combining those together, I've got J26. And then if I combine all the I2 and I3 terms together, I've got, moving those to the other side, negative 5 plus J9 times I2 minus J5 I3. All right, I've got another equation down. Next, I move to loop number 3. In loop 3, I have a 10, a J8, and a minus J5. So let's start with that. I've got 10 I3, then I've got plus J8 I3 minus I1 minus J4, oh, sorry, my bad, J5 I3 minus I2 equals to 0. Again, I can sub in 4 here. And so I've got the following. I've got 10 I3 plus J8 I3 minus J32 minus J5 I3 plus J5 I2 equals to 0. So let's collect these terms together. All of my I2s are just going to be J5 I2 plus 10 plus J3 I3 is equal to J32. Now, since I already know the solution to equation 1 there, I can move from that to solve for I2 and I3 in MATLAB or Python or algebraically. So let's just use equations 2 and 3 to solve for I2 and I3. When I do that, I've got minus 5 plus J9 minus J5, and then I've got J5, and then 10 plus J3, and this is I1, I2, or sorry, take that back, I2, I3 is equal to J16, J32. Go back, sorry, not J16, that's J26 and J32. For step 4 is to solve, so let's go ahead and do that. Plugging this into Python or MATLAB or whatever actually likes to work with my complex numbers here, I'll get 2.78 angle negative 11.2 degrees, and I'll get 1.778, I guess 1.78 angle 81.69 degrees. Of course, these are measured in amps. I'm not really done because I asked for the value of I naught, and I said I naught is equal to negative I2. So I naught equals negative I2, which is equal to 2.78 angle negative 11.2 degrees, and then either plus or minus 180 degrees. Why don't we go ahead and, I don't know, add 180 degrees? If I add 180 degrees, what do I get? I get 2.78 angle 168.8 degrees amps. And now I don't need to do step 5 because I asked for things in the phasor domain, but I have a pretty decent answer. 2.78 angle 168.8 degrees amps. All right, that's all I'm going to cover for nodal and mesh analysis in AC. If you are very comfortable with doing these in DC, the only thing that's different about them is that I have complex numbers instead of real numbers, which just makes things a little bit more difficult algebraically, but conceptually it is still the same. All right, that's all I've got for this one. Thanks for watching.